Under normal conditions, light is incredibly polite. It obeys a rule in physics called the principle of superposition. If you shine two beams of light at each other, their waves pass right through one another in a straight line. They don't interact, they don't bounce, and they don't change color. That predictable, linear behavior was accepted as a rule of nature until 1960. The invention of the laser gave scientists a way to concentrate electromagnetic fields to intensities that had never been observed in a laboratory. When you cross a threshold of about 100 million volts per meter, the rules break. At that intensity, light rivals the electrical forces holding atoms together. The material's electron cloud stops oscillating smoothly like a spring and begins to warp, responding nonlinearly. Crossing this threshold doesn't destroy the light, it makes the beam malleable. It gives us the physical leverage to rewrite the frequency, phase, and path of the light itself. In 1961, Peter Franken and his team at the University of Michigan decided to test this new leverage. They fired an intense, invisible infrared laser into a quartz crystal. What emerged from the other side was a distinct beam of visible green light. They had successfully demonstrated second harmonic generation. Inside that crystal, the quantum math is a trade-off. Two lower-frequency, infrared photons are destroyed, and their energy is fused to create a single new photon. This new photon has exactly twice the frequency and half the wavelength of the originals. By doubling the frequency, Franken's team proved that the color of a light beam was no longer a fixed constant. It was a property we could manipulate. Today, those laboratory experiments have scaled into a $1.21 billion global industry. Nonlinear optics is now the hidden engine driving modern infrastructure. This chart tracks a 9.2% compound annual growth rate. By 2034, the market is expected to reach $2.67 billion, with the vast majority of that value concentrated in telecommunications. Sustaining that growth requires discovering and manufacturing specific crystals and polymers that can survive being bombarded by these intense laser blasts without shattering. A primary material for the job is an inorganic crystal called beta-barium borate, or BBO. It is valued because it remains transparent across a massive range of wavelengths and has a remarkably high threshold for optical damage. These crystals aren't just lab supplies, they are the essential hardware required to scale the next generation of global data links and high-speed communications. Before you can put a crystal into a commercial machine, you have to find the exact point where it begins to bend and absorb light. This schematic outlines the gold standard for testing, the single-beam Z-scan method. By sliding a sample through a tightly focused laser beam, engineers can measure how light transmission changes, allowing them to calculate the material's exact nonlinear refractive index. This data is vital because things like frequency doubling are parametric processes. The conversion happens instantly, without changing the crystal's quantum state. This conversion has a flaw. Green and red waves travel at different speeds. Falling out of sync creates destructive interference, canceling the output. Engineers fix this using phase matching. Tilting the laser locks both waves in perfect sync, stacking their amplitudes into a massive signal. Mastering phase matching turned a chaotic physics anomaly into a reliable engineering tool. That tool arrived just in time. Global 5G data traffic is compounding at 28% every single year, pushing fiber optic cables to their absolute physical data limits. To manage the load, network operators use dense wavelength division multiplexing. Nonlinear frequency converters squeeze 300 to 500% more capacity into those same physical fiber arrays. In medicine, standard microscopes hit a physical wall at about 50 micrometers deep into tissue, where light scatters and the image blurs. Multiphoton microscopy bypasses that wall. Instead of a single blue photon that scatters at the surface, a laser fires two red infrared photons. They travel 1,000 micrometers deep before fusing into a single visible photon right at the target site. By manipulating the frequency of light, we prevent the need for billions in new cables and allow doctors to detect melanoma deep below the skin without an invasive biopsy. As we rapidly approach the absolute limits of traditional computing power, the focus is shifting entirely toward quantum systems. Inside these architectures, BBO crystals are already generating the entangled photon pairs that provide the physical framework for quantum information networks. It is an immense leap from where this started. Two-photon absorption was first predicted in 1931 by Maria Geppert-Mayer as a purely theoretical curiosity. For decades, her math remained untested, but as laser power caught up to her equations, her 1931 theory became the operating manual for the fiber networks and medical imaging systems we use today. When scientists pushed light past its physical breaking point, they didn't break the universe, they accessed the hidden mechanics required to build a quantum future.